Picture the Earth from a great height, floating quiet and blue against the dark. It looks the same as it does today. The oceans still curve along the coasts. The clouds still drift in slow white bands. But if you could drop down through those clouds 250 million years ago and take one breath, your body would fail within minutes. Not because of cold or heat or any monster in the water. The air itself would not hold enough oxygen to keep you alive. This is the world we are going to sit with tonight. A world that looked familiar from far away and was almost entirely unlivable up close. Geologists call this time the end of the Permian period, the edge of a change so slow that nothing alive could have felt it happening day to day. It unfolded across hundreds of thousands of years, and when it was done, close to 9 out of every 10 species in the ocean were gone. On land, the losses were almost as deep. We are not talking about an asteroid or a single terrible night. This was slower than that, and in some ways stranger. The air changed, the oceans changed, the temperature crept upward in increments too small for any single animal to notice in its own lifetime. And somewhere in that slow drift, the chemistry of breathing itself turned against nearly everything alive. Before we go further, the planet has a new quiet wonder to share every night. If you'd like one waiting for you each evening, subscribe and let it come to you. Tonight, we are going to move through this lost world slowly, the way it actually happened. Not as a disaster with a clear beginning and end, but as a long, uneven drift. Scientists still argue about exactly what set it off. One leading idea points to a stretch of massive volcanic eruptions in what is now Siberia, pouring out lava and gas for perhaps 1 million years, thickening the sky with carbon dioxide and sulfur. Another line of evidence suggests methane, released from the seafloor or from coal deposits set alight by that same volcanic heat, may have added its own weight to the warming air. The two ideas are not opposites. Many researchers think several causes braided together, each one making the others worse, though the exact sequence remains an open question. What we do know, from layers of ancient rock, is what the air was becoming. Oxygen levels, which had supported large active animals for tens of millions of years, began to fall. Carbon dioxide climbed instead, and with it came heat, and with the heat came changes in rainfall, in ocean chemistry, in the layers of gas pressing down on every living thing. If you had stood on a Permian shoreline as this unfolded, you likely would not have seen anything dramatic in a single afternoon. The sky might have looked hazy, the sun a little duller, through volcanic dust drifting from half a world away. It is the kind of change a person could live inside and barely notice, the way you don't notice a room slowly losing its light at dusk. But your lungs would have noticed. Thinner oxygen at sea level would have felt like breathing on a high mountain, without ever climbing one. Every breath would have asked more of you and given you less in return. There was no single moment of alarm, no visible line between before and after. There was only a slow tightening, generation after generation, as fewer young survived, as familiar food grew scarce, as the water and air asked something that could no longer be given. This is part of what makes the end Permian event so hard to picture, and so worth sitting with in the dark. It did not look like an ending while it was happening. It only looks like one now, from far enough away, with enough rock and time between us and it. Across the sections ahead, we will walk through that ancient air, degree by degree, gas by gas. We will look at oceans losing their oxygen from the bottom up, and at the long, quiet stretch of years that followed, when the world was recovering, but still merely silent. None of it will resolve neatly. Much of it remains genuinely unknown. For now, It is enough to picture that blue, familiar-looking planet from far away, and to remember that familiar does not always mean survivable. Let's start with something simple. The sky above you right now is blue. That blue comes from sunlight bouncing off tiny gas molecules, mostly nitrogen and oxygen, scattering short blue light in every direction. It is such a small thing to notice, but 250 million years ago, that blue would have looked different. The air itself had changed, and to understand why, we need to start with what air actually is. Air is not one thing. It is a mix, a thin envelope of gas wrapped around a rock that is spinning through space. Today, that envelope is about 78% nitrogen and 21% oxygen, with small traces of other gases filling in the rest. This mix took billions of years to build. It did not arrive all at once. It grew slowly through the quiet work of tiny living things and the equally quiet churn of rock and fire below the ground. Picture the whole atmosphere squeezed down into something you could hold. If you gathered every gas molecule above your head into a column reaching up 60 miles, and then imagined that column standing on a bathroom scale, it would weigh close to 15 pounds, pressing down on every square inch of you. Do not feel this weight because your body pushes back with equal force from the inside. It is a balance so constant that you have never once had to think about it. 250 million years ago, near the end of what scientists call the Permian period, that balance began to shift. The change was not sudden, not in the way a storm arrives or a wave breaks. It moved across hundreds of thousands of years, maybe longer, driven by one of the largest volcanic events the planet has ever produced. Molten rock poured out across what is now Siberia, covering an area close to the size of the continental United States. Some estimates say larger. This was not one eruption. It was a long series, pulsing on and off for perhaps 1 million years, filling the sky with gas the way a leaking pipe slowly floods a basement, unnoticed until the water is at your ankles. Carbon dioxide built up in that ancient air. So did sulfur gases, and possibly methane released from ocean sediments as the world warmed. Some researchers estimate carbon dioxide levels climbed several times higher than what surrounds you tonight. Others argue the rise was less extreme, but combined with other stresses, like heat and falling oxygen, to create the same result. The exact numbers remain a subject of real scientific debate, pieced together from ancient rock, fossil chemistry, and careful patient argument. What would this have meant for a body like yours? Breathing air with much higher carbon dioxide feels different long before it becomes dangerous. Your breathing rate would rise without your permission. A dull heaviness would settle behind your eyes. If the change happened over years, your body might adjust, the way people who move to high mountains slowly adjust to thinner air. But this change did not happen over years. It happened over spans of time longer than every human civilization combined. Stretched again and again, no body, no lineage, had the luxury of adjusting in a single lifetime. The adjusting, if it happened at all, happened across generations of creatures who never knew the world had once been different. Here is where the sky comes back in. A thicker blanket of certain gases changes how sunlight moves through the air and how heat leaves the ground at night. Some scientists believe the sky itself may have looked slightly different during this period. Hazier, perhaps duller in color, shaped by fine volcanic particles drifting for years after each eruption. Others caution that we cannot know the exact color of an ancient sky with certainty. We can only work backward from rock and ash and chemistry, building a careful guess. What is not in question is the direction of change. Oxygen, available to breathing creatures, slowly declined in many environments, while heat-trapping gases slowly rose. This is the basic shape of the mystery this episode sits inside. Not a single dramatic event, but a slow tilting of the table, so gradual that no single creature alive at the time could have pointed to the moment things turned wrong. It simply grew a little harder to breathe, a little warmer to live, year after year, for longer than we can easily picture. We will return to this air again and again tonight, because the story of the end Permian world is in many ways the story of a sky that quietly stopped being kind. For now, simply picture it: a pale sun, a sky perhaps thinner in blue, a fraction heavier in haze, and beneath it, an entire planet breathing air that was slowly becoming something else. Long before the world your body could not have survived, there was a world your lungs would not have recognized at all. Go back far enough, past 2 billion years, and you find an Earth with almost no oxygen in its air. The sky was not blue then. It may have carried a faint orange haze, thin and strange, drifting over oceans that held no fish, no coral, no green anything you would call familiar. If you had stood on that shore, you would have suffocated within minutes, not from poison, from absence. There was simply nothing there for you to breathe. The change that made our air breathable did not happen quickly. It happened slowly over hundreds of millions of years in what some scientists call the Great Oxidation Event. Tiny organisms in the ocean, ancestors of modern cyanobacteria, had learned a new trick. They used sunlight to split water apart, releasing oxygen as a byproduct. This is the same basic process modern plants still use. At first, the ocean and the rocks soaked up nearly all of it. Iron in the seawater rusted, sinking to the ocean floor in thin red layers we can still read in stone today. Layers striped like the rings of a very old, very patient tree. Only after those iron sinks became full did oxygen begin to build up in the air itself. This took an extraordinarily long time, perhaps 300 million years from the first hints of oxygen to a sky that held a real breathable amount. 300 million years is longer than the time since the extinction that will occupy much of tonight's story. It is a stretch of time so vast that comparing it to a human life feels almost meaningless. And yet, geologically, it happened in what we might call a hurry. Before that slow storm of oxygen, life had gone without it for well over 1 billion years. The strange part is that this new oxygen, the very thing your body needs to survive, was likely a catastrophe for much of the life that existed at the time. Oxygen is chemically reactive. It breaks down organic molecules. For organisms built to live without it, oxygen would have acted like a slow poison, seeping into a world that had never needed defenses against it. Some researchers call this the planet's first great extinction, quieter than the one still ahead of us in this story, but no less total for the microbes it affected. Whole lineages of oxygen-intolerant life may have been pushed into the deep mud, the low oxygen pockets, the corners of the earth where the old rules still applied. Some still live there today, in stagnant sediment and airless trenches, breathing chemistry instead of air. Why did this shift happen when it did, and not earlier or later? That remains an open question. One theory points to the evolution of oxygen-producing microbes themselves, arguing that once life discovered this trick, the build-up was almost inevitable. A competing idea focuses on the planet, not the microbes, suggesting that Earth's chemistry needed to change first. Volcanic activity may have shifted the mix of gases escaping from the crust. The continents may have arranged themselves differently, altering how much organic carbon got buried versus how much oxygen escaped into the sky. Perhaps both stories are true at once, the biology and the geology moving together, each nudging the other forward across a span of time too slow for any single witness to see. What is fairly well agreed upon is the outcome. Oxygen accumulated. It rose from a trace gas to a defining feature of our atmosphere. It eventually reached levels that allowed larger, more complex life to exist at all, since bigger bodies need more efficient ways to burn fuel and move. Without that ancient storm of gas, slow and invisible as it was, none of what came later could have followed. Not the coral reefs, not the forests, not you. It is worth sitting with the size of that transformation for a moment before we move forward in this story. The sky above you tonight, calm and dark and full of air you never think twice about, was once completely unlike this. It took a mistake or an invention made by the smallest living things on the planet, sustained over hundreds of millions of years, to build the atmosphere your body now depends on, without a second thought. And if the balance shifted again in either direction, too much oxygen or too little, your body would not adjust. It would simply stop working, the way a fire stops working without enough air, or burns too fast with too much. The air you trust completely tonight was not always here, and it was not guaranteed to arrive at all. Picture the ocean 250 million years ago, in the time we now call the end of the Permian period. It looked blue from far away, the way any ocean looks blue, but close to the surface, something was changing in the water itself. The sea was slowly turning sour. Carbon dioxide, pouring out of volcanoes for thousands of years, was dissolving into the waves. Slowly, patiently, it was turning seawater into something closer to a weak acid. This matters more than it sounds like it should. Carbon dioxide and water make carbonic acid, the same mild acid found in a glass of soda water. In small amounts, the ocean can absorb this and stay in balance. But the volcanic outpouring at the end of the Permian was not small. It went on for tens of thousands of years, maybe longer, adding gas faster than the sea could buffer it. The water grew more acidic, degree by imperceptible degree, the way a room grows cold after a door is left open. No one alive then could have felt the shift day by day, but across centuries, it built into something the ocean itself could not shrug off. Bone and shell are both built from calcium carbonate, a mineral that forms easily in ordinary seawater. It is the same basic material in a clamshell, a coral skeleton, a fish's inner earstone. Under normal conditions, the ocean is full of the ingredients this mineral needs, but add enough acid, and those ingredients get harder to piece together. Some creatures found it harder to build shells at all. Others found their shells slowly dissolving, the mineral pulled apart faster than their bodies could replace it. If you had held a piece of coral from those seas in your hand, it might have felt soft at the edges, like chalk left out in the rain. This is one of the leading theories for why the end Permian extinction hit shelled and skeleton-building ocean animals so hard. Trilobites, a group of armored sea creatures that had thrived for nearly 300 million years, vanished completely. Many kinds of coral disappeared, but the theory is not the whole story, and researchers are careful about that. Ocean acidification alone does not explain everything that died, especially on land, where there was no seawater to turn sour. Some researchers think the acidification worked alongside a second and third force, rising heat and dropping oxygen. Others argue the timing does not line up perfectly everywhere the evidence has been checked. The rock layers from this period are thin and hard to read with certainty, so the exact sequence of events remains an open question. What we can say is where the ingredients came from. The calcium in every shell, every human bone, traces back to stars. Calcium forms inside massive stars near the end of their lives, built up through nuclear fusion, then scattered across space when those stars finally exploded. That calcium drifted for billions of years before some of it became part of the cloud of dust and gas that formed our solar system. The carbon in carbon dioxide has a similar story, forged in the same dying stars, carried across unimaginable distances before settling into the rock and air of a young Earth. Even the water in that ancient, souring ocean may have first arrived here on icy comets and asteroids, delivered over millions of years early in the planet's history. Everything in that sea, the acid and the shells and the water itself, had already traveled farther than any living thing ever will. If you had stood on a Permian shoreline and reached into the shallows, the water would have felt ordinary at first touch. You would not have tasted the difference. But if you left a shell resting on the sand for a season, you might have watched it slowly lose its shape, the way a lump of sugar softens in tea. Nothing about it would have looked violent. It would have looked like patience, and it would have taken more patience than any single life could offer. The open question that remains is not whether the acid was real. The rock record shows chemical fingerprints that many scientists agree point toward it. The question is how much weight to give it compared to the heat and the airlessness building at the same time. Was the sour ocean the main actor, or one voice in a chorus of dying? No single layer of ancient rock gives a full answer. The sea kept its secrets well, the same way it keeps most things, folded quietly into stone, and waiting for someone patient enough to ask. Picture the ocean near the end of the Permian period, 250 million years ago. From above, it might have looked calm, blue water, soft waves, the same slow rhythm oceans always keep. But under the surface, something was changing that no eye could see happening in real time. The water was losing its oxygen, layer by layer, like a room slowly filling with smoke from the bottom up. This process is called ocean anoxia, which simply means water, with little or no oxygen dissolved in it. Fish, corals, and shelled creatures need that oxygen the way you need the air around you right now. Take it away slowly enough, and there is no single moment of crisis. There is only a long, quiet erasure. If you had been swimming in those waters, you would not have felt a sudden change. You would have simply run out of breath a little sooner each day, in a world that never explained why. One force driving this was heat. Massive volcanic eruptions, likely centered in what is now Siberia, poured out lava and gas for thousands of years. This released enormous amounts of carbon dioxide into the sky. Carbon dioxide traps heat, and over time, the oceans absorbed that heat and grew warmer. Warm water holds less oxygen than cold water. This is a simple physical fact, the same reason a warm soda goes flat faster than a cold one. As the seas warmed, they lost their capacity to hold the gas that life depended on. But heat was not the only force at work. Warmer water also becomes more stratified, which means it separates into layers that do not mix easily. Cold, oxygen-rich water usually sinks and circulates, carrying life's breath down into the depths. When the surface stays warm for long stretches, that circulation slows or stops. The deep ocean becomes cut off, sealed away from fresh oxygen like a basement with the door shut down there. In the dark, the water may have turned anoxic first and stayed that way longest. Some researchers believe this stagnation was the main driver of the extinction, spreading upward from the depths like rising water in a flooded room. Others argue the story is more tangled, that anoxia was one piece among many, working alongside acidification and heat, rather than acting alone. The sediment records from this period, layers of ancient rock that hold chemical clues, show signs consistent with widespread low oxygen. But scientists still debate how fast it spread, how deep it reached, and whether it struck all oceans evenly or crept unevenly across the globe. The rock does not always tell a simple story. There is also the matter of sulfur. In water with no oxygen, certain bacteria thrive by using sulfur instead. These microbes can produce hydrogen sulfide, a gas that is toxic to most animal life and gives off the smell of rotten eggs. Some scientists propose that hydrogen sulfide may have bubbled up from these anoxic depths in large amounts, poisoning shallow waters and even drifting into the air above the sea. This idea remains a hypothesis, supported by some chemical evidence in old rock layers, but not universally accepted. If it happened, the ocean itself would have become a source of the very poison working against the life within it. And then there is the rust. Iron behaves differently in water with no oxygen. It stays dissolved instead of binding with oxygen to form the reddish, solid particles we associate with rust. Geologists have found bands of iron-rich rock from this era that suggest the ocean, in places, may have turned a strange, sickly hue, greenish or reddish-brown, as dissolved iron built up in the water. Picture standing at the edge of such a sea. The waves would still move, the horizon would still curve away into grey light, but the water itself might have carried a strange tint, evidence of unseen chemistry working through it. None of these forces acted alone. Heat, stagnation, sulfur, and iron chemistry likely intertwined across thousands of years, each one nudging the others further from balance, untangling. Exactly how they combined is one of the enduring puzzles of this extinction. The ocean did not fall apart in a moment. It shifted chemically, layer by layer, for longer than any single human life could measure. Whatever finally tipped the balance toward near total collapse remains an open question, one written in rust-colored stone and read very slowly, one careful layer at a time. Let's step back from the Great Extinction for a moment and think about scale. Not the scale of one bad century, but the scale of an Earth that could freeze itself nearly whole and stay that way for longer than your mind can comfortably hold. Picture a single year of your life. Now picture 1,000 of those years laid end to end. That is still just a heartbeat compared to what we are about to describe. Long before the world of poisoned air and choking oceans we have been sitting with, Earth passed through several ice ages so severe that some scientists call them Snowball Earth events. The idea is this: ice may have spread from the poles all the way to the equator, wrapping the planet in white and blue. One long unbroken sheet of frozen ocean and frozen land. If you shrank the entire history of Earth down to a single calendar year, with the planet forming on January 1st at midnight, these deep freezes would fall sometime in July. Humans would not appear until the last few seconds of December 31st. The freeze itself, in that condensed year, might last for what feels like a single day. In real time, it lasted for millions of years, 10 million, perhaps longer, long enough that generations of any surviving life would never have known open water or a warm season or a sky without haze. Try this comparison instead. If the coldest part of that frozen stretch were shrunk down to the length of one night's sleep, 8 hours, then the cold snap after the extinction we have been discussing, that quieter and shorter chill, would only take up a few minutes near the end. The Snowball Earth periods dwarf almost everything else in this story. They are the long night against which all our other long nights get measured. One leading idea about why this happened points to the sun itself. Very early in Earth's history, the sun burned about 30% dimmer than it does today. Less heat reached the surface. At the same time, some researchers propose that a drop in volcanic activity meant less carbon dioxide entering the sky, and carbon dioxide is one of the gases that holds heat near the ground, the way a blanket holds your own warmth close to your skin. With a fainter sun and a thinner blanket, ice could have crept outward from the poles and kept spreading, because ice reflects sunlight back into the sky, which cools things further, which grows more ice. It is a loop that once started may be hard to stop. But this picture has real gaps. Some geologists studying ancient rock layers see signs that patches of open water may have survived even during the coldest stretches. Meltwater pools or slushy seas near the equator. If that is true, the planet may never have been a true solid snowball at all, just a world wearing a very heavy, very long-lasting coat. The evidence sits in thin bands of old seafloor rock, pushed up and exposed after hundreds of millions of years. And reading those bands clearly is difficult work. Both pictures, the total freeze and the partial freeze, remain on the table. If you stood on the shore during one of these long freezes, there would be no shore to speak of. Only ice meeting ice at some line you could not find. The cold would reach your bones in minutes, long before you had time to feel afraid of it. Your breath would freeze against your face. The silence would not feel peaceful. It would feel total, the kind of quiet that has no birds in it, because there are no birds yet. No wind through leaves because there are no leaves. Just the low groan of ice, shifting somewhere far off. A sound with no living answer. What finally ended these frozen ages is its own open question. One idea holds that volcanoes, still erupting beneath all that ice, slowly built up carbon dioxide in the air over millions of years, until the blanket grew thick enough to finally melt the coat from below. Another idea wonders whether the timing had more to do with shifting continents, changing how ocean currents moved heat around the globe. Neither answer is proven. Both may have played some part. We carry these frozen ages with us, mostly as a sense of scale, a way to measure how patient the Earth can be with its own transformations. The extinction we have been following, the one that emptied oceans and thickened the air with poison, unfolded over a span that still fits just barely inside human imagination. The Snowball Earth periods do not. They ask us to imagine ice with no memory of green, held for a length of time that makes our own species look like a passing thought. Long before the great dying that would end the Permian world, the sun above Earth was strange in a different way. It was fainter, not by much, but enough to matter. Stars like our sun grow brighter as they age, burning slowly hotter over billions of years. Go back far enough, and you find a sun that gave less warmth to a planet that still needed to stay livable. If you stood on the ancient surface and looked up, you would see a familiar white disk in the sky. It would not look dim to your eyes, but the total heat reaching the ground would be lower than what we feel today. Some researchers call this the faint young sun problem. It is one of the oldest open questions in Earth science, and it is still not fully settled. Here is the puzzle at the center of it. A weaker sun should have left early Earth, locked in ice, a frozen ball with no liquid water at all. Yet the geological record shows the opposite. There are ancient riverbeds carved into stone. There are signs of oceans that stayed liquid for enormous stretches of time. Something kept the surface warm enough for water to flow, even while the sun gave less heat than it does now. One leading idea points to greenhouse gases, those atmospheric compounds that trap heat the way a blanket holds warmth against skin. Early Earth likely held far more carbon dioxide and methane in its air than it does today. Thicker blankets of these gases could have made up the difference, holding in warmth that a fainter sun could not supply on its own. If you stood in that ancient air, each breath would taste faintly sharp, thick with gases your lungs were never built to sort through calmly. But this answer creates its own smaller mystery. The exact mix of gases needed to balance the weak sun is hard to pin down. Rock samples from those early periods are rare, worn down by billions of years of geologic churn. Scientists have to read clues from ancient soils, old mineral grains, and chemical traces left in stone. Reading those clues is a little like listening to a whisper through a thick wall. The message is there, but never perfectly clear. Another idea suggests the early atmosphere might have held more nitrogen than it does today, which can also change how heat moves and lingers near the surface. Thicker air of any kind changes pressure, and pressure changes how warmth behaves. Under such a sky, sunsets might have looked heavier somehow, the light bending through denser air before touching the ground. No one can say for certain what color that sky would have shown you. Some models suggest a duller, more orange cast to daylight, though this remains speculative. Picture standing on a shoreline during this era, one that would return in a very different form after the extinction millions of years later. Waves would lap at dark volcanic rock, and the air above the water would feel warm despite a sun giving less energy than the one you know. If you spread your hand against the ground, the stone might already feel sun-warmed by late morning, even under that fainter light. The heat would come not just from above, but from an atmosphere working harder to hold it in. This faint sun question circles back to the extinction event that reshaped the Permian world, because it shows how fragile the balance of temperature has always been on this planet. A sun too weak could freeze the oceans solid. Gases too thick could overheat them instead. Earth has spent its whole history walking a narrow line between those two outcomes, adjusting through feedback loops that operate over spans of time too slow for any single lifetime to notice. The recovery period after the Permian extinction shows this balance breaking down in the other direction, with too much heat trapped rather than too little. But the deep past reminds us the opposite danger was just as real. A planet can lose its warmth as easily as it can gain too much. Both paths lead to conditions no soft-bodied creature could survive for long. No one living today can say with full confidence how Earth solved the faint sun problem. The leading answers involve greenhouse gases, but the fine details remain open, argued over by researchers comparing rock chemistry from opposite corners of the globe. It stays an unresolved question, resting quietly beneath every warmer, more familiar sky we now take for granted. Go down, far enough into the rock, past the reach of roots and burrowing things, and you find the record of a heat that lasted for centuries. This is where the story of the great dying 250 million years ago becomes something you can almost touch deep beneath what is now Siberia. Magma pushed up through the crust in slow, relentless pulses. Geologists call this event the Siberian Traps, a stack of lava flows so vast that its remains still cover an area close to the size of Europe. If you tried to walk across it, the walk would take longer than most human lives. The heat did not arrive as a single burst. It came in waves over what may have been close to 1 million years, though the exact span is still argued over. Each pulse pushed lava across the surface and pumped gas into the sky above. The layers of basalt rock, when you look at them today, sit stacked like pages in a very slow book. Some of those pages are many meters thick. Each one represents a flow that took months or years to cool. One theory holds that the true damage was not the lava itself, but what it burned along the way. Siberia, at the time, sat over deep beds of coal and salt and organic rock. As magma moved through these buried layers, it may have baked them, releasing carbon dioxide, methane and sulfur gases in enormous quantities. Some researchers picture this as a slow-motion furnace running for tens of thousands of years, breathing gas into an atmosphere that had no way to clean itself quickly. Other researchers focus less on the buried fuel and more on the sheer volume of the eruptions themselves, arguing that the lava and its gases alone were enough. The two ideas are not fully separate, and many scientists suspect both processes work together. Which one mattered more remains open. If you had stood near the edge of this region during an active phase, the ground under your feet would have carried a heat you could feel through your shoes long before you saw any fire. The air would have smelled sharp, metallic, and faintly rotten from sulfur gases drifting on the wind. Rain, when it fell at all, may have carried enough acid to sting bare skin and strip the color from anything green nearby. Your body could not have lasted long in that air. The lungs are not built for a sky that heavy. Deeper still, below the lava itself, lies the question of what triggered the whole event. Some geologists point to a mantle plume, a rising column of unusually hot rock that pushes up from far below the crust, like a slow flame under a pot. Others wonder whether the plume alone explains the scale of what happened, or whether something in the crust above it was already weakened, already primed to crack open under pressure. The mantle plume idea remains the leading explanation, but even its supporters admit the fine details, the exact plumbing, are still guesswork built from indirect clues. What makes this chapter of the story feel almost ghostly is the timescale involved. A volcano erupting in a single afternoon is a shape the human mind can hold. A furnace running underground for centuries or longer is not. The rock layers do not scream or rumble in the way our imagination wants disaster to sound. They simply accumulate, one flow at a time, until an area the size of a continent has been reshaped without a single generation of anything alive ever seeing the whole event. If you multiplied every hour you have lived by many thousands, you still would not reach the span some of these eruptions may have covered. The chemical fingerprints of this event show up far from Siberia. Carbon isotopes in rock layers from China to South Africa shift at the same geological moment, suggesting the gases spread worldwide, changing the makeup of both the air and the sea. Whether the shift was fast enough to be called sudden in geological terms, or whether it crept in more slowly than once believed, is still being measured and remeasured. Newer dating techniques keep narrowing the window, but they have not closed it. What remains certain is that something in the deep rock of Siberia holds a kind of memory. Yet, it remembers heat sustained far longer than any furnace built by human hands, gas released in volumes hard to picture, and a slow chemical drift that reached oceans thousands of miles away. Whether it was the single cause of everything that followed, or one heavy hand among several, is still being worked out, layer by careful layer. Long before the world grew too hot to breathe, it had another rhythm entirely. It grew cold, not the gentle cold of a winter night, but a cold that wrapped the whole planet in ice, from pole to pole, for millions of years at a time. Scientists call these events Snowball Earth periods, and the evidence for them sits quietly in ancient rock, in the striped scratches that glaciers leave behind, found today near the equator, where no ice should ever have reached. Picture standing on a shoreline during one of these ages, perhaps 700 million years ago, long before the extinction that later emptied the seas. The ocean in front of you would not move like water, you know. It would be sealed under ice thick enough to swallow mountains. Some researchers think over a kilometer deep in places. Sound would not travel the way it does now. Your own breath would freeze into fog and vanish into a silence, with no birds, no waves, no wind moving through leaves, because none of those things existed yet to make a sound at all. The cause of these deep freezes remains one of the open questions of Earth's long history. One idea points to the sun itself. Early in the planet's life, the sun burned about 30% dimmer than it does today, a puzzle researchers call the faint young sun problem, with less warmth arriving from above. The balance of the atmosphere mattered even more than it does now. Another theory focuses on carbon dioxide, the same gas that would later climb far too high before the Great Extinction. If levels dropped low enough, the greenhouse effect that keeps our planet warm could have weakened enough to let ice creep down from the poles and never stop. Once ice covers enough of the surface, it feeds itself. Ice reflects sunlight back into the sky, instead of absorbing it as warmth. The more ice that spreads, the more sunlight bounces away, and the colder the planet becomes, in a slow tightening loop some scientists call the ice albedo feedback. If you stood at the edge of an advancing ice sheet during one of these ages, you would feel the temperature drop with each mile you walked toward it, the air growing sharper and drier until finally there would be no edge left to stand on at all, only white in every direction. What ended a Snowball Earth event is just as uncertain as what started it. The leading idea involves volcanoes quietly working beneath all that ice for millions of years. Even buried under a frozen ocean, volcanic vents keep releasing carbon dioxide into the air, with no rain to wash the gas away. Since water was locked in ice instead of falling as rain, the carbon dioxide may have built up in the atmosphere for millions of years, slowly at first, then reaching a threshold that finally warmed the planet enough to break the ice apart. Some researchers picture this ending as sudden, a rapid meltdown once the greenhouse effect became strong enough. Others think the thaw came in fits, false starts, partial retreats and returns, before a final, full recovery. These freezes and thaws are not remembered the way the later extinction is, since they came before most complex life existed, to leave a rich fossil record of loss. But they set a pattern the planet would return to. Cycles of extremes, long stretches where conditions on the surface would have offered nothing gentle to any body evolved for the world we know. A creature built for our climate, dropped into a Snowball Earth winter, would lose feeling in its hands within minutes and its life within an hour. The same is true, in reverse, of the hothouse world that came later, during the extinction 250 million years ago, when the air grew too warm and too short of oxygen for a body like yours to manage even resting still. What connects these cycles, cold and hot alike, is the same quiet truth. The planet does not hold steady for the comfort of anything living on it. It swings over spans of time too long for any single creature to notice, between states that would kill almost everything alive today. Some of these swings came from the sun's own slow brightening over billions of years. Others came from gases trapped or released from inside the Earth itself. Whether these two forces worked together or took turns driving the planet from one extreme to another is still debated among the researchers who study these ancient rocks. The ice ages we mention on this channel from time to time, the ones within human memory, are gentle ripples by comparison. What came before them was something else entirely, a set of rhythms the Earth once beat out alone, with no one there to listen. "250 million years ago, the air itself was changing, and it was not changing alone. Every part of Earth's surface was tied to every other part, the way rooms in a house share the same failing furnace. The oceans, the sky, the rock underfoot, all of it moved together during this slow unraveling. To understand the thin, difficult air of that time, you have to think about what was happening just beyond it, in the water below and the stone below that picture. The ocean as a series of floors in a very tall building. Warm water sits near the top, where sunlight reaches. Cold water sits near the bottom, in the dark. In a healthy ocean, these floors mix. Storms churn the surface. Currents carry cold, oxygen-rich water down and push warmer water up. But during this period, the mixing slowed. The deep ocean grew still, and stillness let oxygen drain away from the depths without being replaced. The change below the waves helped shape the air above them, because ocean and atmosphere trade gases constantly, breathing on each other across the water's surface. One theory holds that as the oceans lost oxygen, they also released more carbon dioxide into the sky, thickening the air in a way that made it harder for creatures on land to get enough oxygen with each breath. A competing view suggests the land and sea crises had separate triggers driven by different volcanic pulses and simply arrived close together in time. Both ideas agree on one thing: whatever happened in the water did not stay in the water. The neighboring systems, sea and sky, were locked together, each one pushing the other further from balance. Volcanic activity, likely centered in what is now Siberia, poured gas into the atmosphere across thousands of years. This was not one eruption. It was a long, low exhalation from the Earth, gas accumulating faster than plants and oceans could absorb it. If you had stood at the edge of a forest during this time, the air moving into your lungs would have carried a different mix than the air we breathe now. Some researchers estimate the oxygen available at sea level may have dropped enough that breathing at what is now sea level would have felt like breathing partway up a tall mountain. Every step would have asked more of your heart and lungs than it does today. This thinning air had neighbors of its own making. Warmer temperatures held less dissolved oxygen in water, which weakened the ocean further, which released more gas into the sky, which warmed the air more. Round and round it went, each system leaning on the one beside it. Scientists sometimes call this kind of chain a feedback loop, meaning a change that makes more of itself happen. The evidence for this particular loop comes from chemical traces left in ancient rock layers, tiny signatures of carbon and sulfur that hint at the gases once swirling above them. The rocks cannot tell us everything. They give a shadow of the story, not the full shape of it. What remains open is how severe the oxygen thinning became in different places and how quickly it happened. Some studies point to a drop steep enough to stress almost every land animal alive at the time. Other studies suggest the change moved slowly enough that some lineages adjusted, breath by breath, generation by generation, over many thousands of years. The honest answer is that both may be true in different regions, since air quality was not the same everywhere on a planet with no true global mixing system to smooth things out evenly. If you had been walking across a floodplain during this stretch of Earth's history, the sky above you might have looked hazy even at midday, thickened faintly by gases drifting from distant eruptions. You would not have seen the danger. You would have simply felt tired sooner than expected, your breath a little shorter on a walk that once felt easy. The neighboring systems of ocean, air, and volcano were quietly rearranging the terms of survival, and the creatures living through it had no way to measure what was happening to them. They only felt its slow pressure, season after season. This is one of the reasons scientists still debate how much of the extinction came from heat, how much from ocean chemistry, and how much from the air alone. The systems were so tangled together that separating one thread from another remains difficult even now. What is agreed upon is that nothing failed by itself. The sky thinned because the ocean starved. The ocean starved because the volcanoes breathed. And somewhere in that chain, the air around every living thing quietly became a little harder to use. $250 million years ago, breathing itself became a slow gamble, not because the air was thin, but because of what filled it. Carbon dioxide levels climbed higher than almost any other point in Earth's long history, driven by volcanic eruptions that poured out gas for what may have been close to 1 million years without real pause. If you had stood on any shoreline during this stretch, each breath would have pulled in air heavier with carbon dioxide than anything a human body has ever known. Your lungs would have worked harder for less reward. Your blood would have carried a faint, constant strain that never eased day after day for longer than any human life could span. The numbers researchers have pieced together from ancient rock and fossil chemistry are staggering to sit with. Some estimates place carbon dioxide levels 5 to 10 times higher than what surrounds us tonight. Ocean temperatures near the surface may have climbed by 10 degrees Celsius or more in the shallow tropics based on chemical signals locked inside ancient shells. 10 degrees sounds small when spoken aloud. Held across an entire ocean, sustained for tens of thousands of years, it becomes something closer to an oven, with the door left permanently cracked open. One theory holds, that the trigger was a stretch of volcanic activity in what is now Siberia, a region where lava did not erupt in a single dramatic burst, but oozed and vented across a span of time longer than agriculture has existed on Earth. The gases released, carbon dioxide chief among them, built up faster than the ocean and atmosphere could absorb or balance them. A competing idea suggests the volcanic gases alone may not explain everything observed in the rock record, and that the burning of buried coal and ancient carbon deposits, ignited by the heat of the eruptions themselves, added a second wave of gas on top of the first. Both ideas agree on the outcome. They differ on exactly how the extremity was built, layer upon layer, like sediment settling on a seafloor. The heat did not arrive as a single wave. It arrived as a slope, rising so gradually that no single generation of any creature would have noticed a difference from one year to the next. This is part of what makes the record so hard to hold in the mind. A change extreme enough to end the vast majority of species on the planet did not feel sudden to anything alive within it. It felt like weather. It felt like the way things simply were, until the way things were no longer supported life at nearly any scale. The most extreme estimates place the ocean's oxygen loss during this period among the most severe in the last 500 million years, turning wide bands of open water into places where breathing itself for anything with gills became difficult or impossible. Researchers studying rock layers from this era, some formed on the floor of what were once shallow tropical seas, have found long stretches with almost no trace of animal burrows or shells. Silence of that kind, spread across whole ocean basins for uncounted thousands of years, has few equals anywhere else in the geologic record. If you had been able to walk along the tide line during the heart of this period, you likely would have found very little sound at all. No birds, since none yet existed. No insects calling from nearby brush. Perhaps only wind and the occasional groan of the sea itself over a shoreline nearly empty of anything moving. The air pressing against your skin would have felt normal in weight, but wrong in a way harder to name. Heavy with gas your body was never built to greet in that concentration for that long. What remains genuinely unresolved is how close this event came to erasing complex life on Earth entirely, and how many separate causes stacked together to produce a single crisis. Some researchers argue the extremity came from one long volcanic exhale. Others believe several smaller triggers compounded each other, each one narrow enough alone, deadly only in combination. The rock record offers fragments, not a full transcript. It tells us the air grew dangerous and the ocean grew still, but not the exact order in which each door closed. What is certain is the scale. This was among the most extreme atmospheric shifts our planet has ever undergone, and it unfolded slowly enough that nothing living within it could have called it a crisis. It simply was the air. It simply was the sea. And somewhere within that unbearable slowness, a small number of lineages found a way to keep breathing at all. Picture a shoreline with no birdsong at all, no insects clicking in the grass, because there is no grass yet, not in the way you would recognize it, just wind, moving over bare rock, and the slow hiss of shallow water lapping against stone. This is the world in the long stretch of time after the Great Dying, roughly 250 million years ago, when Earth's ozone layer, the thin shield of gas high in the sky that blocks most of the sun's ultraviolet light, may have thinned or faltered for a stretch of time that scientists still argue about. The evidence is small and strange. Researchers have found fossilized plant spores from this period with deformities, tiny malformed grains that look burned or scarred, as if something had damaged them before they could ever grow. Some scientists believe this points to a spike in ultraviolet radiation reaching the surface, a kind of exposure no complex land life had faced before. Ultraviolet light, at high enough doses, breaks apart the delicate molecules that carry genetic information. If you stood in that light without shelter, your skin would burn within an hour, and your eyes would ache long before you understood why. But this idea remains contested, and this is one of those places in the story where the details stay small and the disagreement stays real. Other researchers point out that the spore deformities could come from ordinary stress, drought, or volcanic gases irritating living tissue in other ways. The ozone layer is not something anyone could measure directly from that far back. Scientists infer it from clues, from chemistry locked in ancient rock, from statistical patterns in fossil pollen too small to see without a microscope. Nothing here is settled. It is one theory, sitting quietly beside several others, none of them fully proven. What is easier to picture and less argued over is the quiet itself. Whatever combination of poisoned air, warming seas, and possible ultraviolet damage worked together during those years, the result on land was a kind of hush that lasted for what scientists estimate could be millions of years. Forests that once held tall trees with the gentle percussion of falling leaves and the buzz of ancient insects gave way to lower, simpler plant communities. Some places may have held almost nothing green at all for long stretches, just crusted soil and drifting dust, the wind carrying no scent of growth. There is a texture to this kind of silence that is hard to picture until you try. It is not the peaceful quiet of a still night. It is the quiet of absence, the kind that comes when a whole layer of sound has simply stopped being produced, because the creatures who made it are gone. No chorus of small animals at dusk, no rustle of a canopy shifting overhead, just the low sound of wind finding nothing to move but rock and ash. Under a microscope, some of the smallest fossils from this time tell an oddly delicate story. Pollen and spore grains preserved in rock show pitting and thinning in their outer walls, a texture some scientists find almost beautiful in its strangeness, like tiny cratered moons. These grains are only a fraction of a millimeter across, yet they may carry a record of one of the harshest stretches of sunlight the planet has ever produced. Looking closely at something so small, scientists are essentially reading a weather report written 8 generations of ecosystems into the past. If ultraviolet radiation did increase, the mechanism proposed by some researchers involves volcanic chemicals stripping ozone from the upper atmosphere over long, slow spans of time, not in a single event, but as an ongoing condition, decade after decade. Others suggest the ozone layer stayed intact, and the die-off of forests came instead from heat, drought, or carbon dioxide levels most modern plants have never faced. Both explanations point toward the same eerie outcome. Land nearly empty of green things, its low plant cover doing little to hold soil in place. Rivers running heavy with sediment, where roots once slowed the water. You would have felt this world less through danger and more through absence. No shade to stand in, no smell of leaf litter warming in the sun, just open ground and open sky, and a silence that had nowhere left to hide sound, because there was so little sound left to make. Whether the sky above that silence was truly thinner, truly more dangerous with light, is a question written in fossil grains too small to hold, waiting for someone to read them more clearly than we can tonight. For a long time, no one thought to ask about the sky itself. The rocks held clues about oceans and ice and heat, that the air above those ancient oceans left no fossils. It left only faint signals, hidden in chemistry, waiting for someone to notice them. The story starts with a puzzle about the sun. Around 2.5 billion years ago, and again in the stretch of time we have been following tonight, the young sun burned a little dimmer than it does now. Geologists call this the faint young sun problem. If the sun gave less warmth and the air held less of the gases that trap heat, Earth should have been a frozen ball. Instead, the rock record showed liquid water. Something was keeping the planet warm. The search for that something became a search for a very different sky. Early researchers found their first clue in banded iron formations, those thin red and grey stripes of rock you heard about earlier. But a second clue came from something almost invisible, tiny amounts of sulfur trapped inside ancient stone. In the 1980s and 1990s, geochemists studying these sulfur traces noticed something strange. The way the different forms of sulfur, called isotopes, were arranged did not match anything seen in rocks from more recent times. This pattern is now called mass-independent fractionation. It is a technical name for a simple idea. Sunlight itself was rearranging sulfur atoms in the air in a way that only happens when there is very little oxygen and almost no ozone layer above. That detail matters more than it sounds. Ozone, A special form of oxygen high in the sky blocks most of the sun's ultraviolet light before it reaches the ground. Without much ozone, ultraviolet light pours down largely unfiltered. It reaches the ocean surface. It reaches bare rock. It reaches anything living out in the open. If you had stood on that ancient shore at midday, the light itself would have carried a kind of harm your skin has never had to face. Not sunburn as you know it, but something steadier and stranger, working on any exposed cell, hour after hour. Researchers argued for years about how strong this effect really was. One view held that the ultraviolet flood was severe enough to push early life into hiding, favoring organisms that lived underwater or under thin films of mineral and sediment. A competing view suggested the ocean itself. Even shallow water blocked enough ultraviolet light that the danger has been overstated. Both camps agreed on the chemistry. They disagreed on how much it truly shaped where life could survive. That disagreement has never fully closed. The instruments used to find all this were not telescopes pointed at the sky. They were mass spectrometers, machines that measure the tiny weight differences between atoms applied to rock samples gathered from remote outcrops in places like South Africa and Western Australia. Teams spent field seasons chipping ancient stone from cliffs, carrying it home in numbered bags, running it through machines that could detect isotope ratios almost too small to imagine. There were false starts. Some early sulfur readings were contaminated by modern handling or weathering and had to be discarded. Some formations turned out to be younger than first thought, throwing off the timeline piece by piece. Though a picture formed, a sky without enough ozone to shield the ground, a world lit by a harsher version of daylight. Later, other researchers extended this thinking toward the more recent mass extinction we have been circling tonight, the one from about 250 million years ago. Some geochemists proposed that heavy volcanic activity did more than warm the planet and choke the oceans. It may have also damaged the ozone layer of that era, thinning the shield overhead for a time. If true, this would mean the survivors of that extinction were not only enduring heat, add and falling oxygen, they may have also been living under a sky that let in more raw sunlight than their bodies were built for. This idea remains debated. The chemical signals are fainter and harder to isolate than the earlier sulfur clues, and not every research team agrees on how to read them. What stays constant across both stories is the method, patient reading of atoms locked in stone. No eyewitnesses, no photographs, only chemistry standing in for memory. The sky above ancient Earth left no drawings of itself. It left ratios, hidden in rock, waiting quietly for someone with the right machine and enough patience to ask the right question. Even now, some of those ratios are still being argued over in quiet rooms by people who have never seen the sky they are trying to describe. Picture a place called Siberia, though it did not have that name yet. Picture a stretch of land wider than most countries today, cracking open along thousands of miles of fissures. This is not one volcano. It is a wound in the ground itself, and it will not close for a very long time. Most people picture a volcano as a mountain with a single mouth, spitting fire in a dramatic burst. The eruptions that some researchers believe helped unmake the world 250 million years ago looked nothing like that. They were flood basalts, vast sheets of lava that poured out of long cracks in the crust, spreading flat and slow across the land like dark syrup, layer after layer for what may have been close to 1,000,000 years. If you stood at a safe distance and watched, you might not even see fire. you might just see the ground breathing out. The lava itself was not the main danger. The gas was. Each eruption released carbon dioxide, sulfur compounds, and fluorine into the sky in amounts that are hard to hold in the mind. Some researchers estimate the total carbon released may have rivaled or exceeded the carbon humans have added to the atmosphere so far, but stretched across hundreds of thousands of years instead of 2 centuries. The slowness is part of the strangeness. Nothing about it would have looked like a disaster on any single day. Here is one of the details that surprises people most. The lava fields that did this sit on top of the Tunguska Basin, a region rich in coal and salt deposits and organic carbon locked in old rock. As the magma pushed through these layers on its way up, it did not just erupt, it baked the ground around it. Some geologists believe this superheating cooked the buried carbon and salt into extra gas, venting even more into the sky than the lava alone would explain. The eruption did not just poison the air directly, it may have set the ground itself on a slow, invisible burn for centuries, releasing gas from underneath before the lava ever broke the surface. This idea remains a hypothesis tested through the chemistry of ancient rock, not something anyone watched happen. If you had breathed that air, the change would not have struck you all at once. Carbon dioxide levels rose gradually, degree of concentration by degree, over spans of time too long for any one lung to notice. But across centuries, the air over much of the planet may have carried enough sulfur and acid gas to leave a taste in the mouth and a burn in the throat on the worst days near the source. Acid rain, some researchers propose, fell across wide stretches of the world, not as one storm but as a chemical condition of the age. The fog itself is part of the puzzle. Sulfate aerosols, tiny particles of sulfur compounds suspended in the air, can do 2 contradictory things at once. In the short term, they reflect sunlight and cool the surface, sometimes sharply. Over the longer run, the carbon dioxide underneath keeps building and eventually wins out, warming the planet instead. Some scientists think the extinction period may have swung between spells of volcanic cooling and much longer stretches of warming, a stuttering climate, rather than a smooth slide in one direction. Others argue the warming trend dominated the whole event, and the cooling spells were brief, minor interruptions. The layered rock evidence does not yet settle which pattern is closer to true. What almost nobody expects is how ordinary the sky may have looked most of the time. Not black with ash, not glowing red, just faintly hazy, day after day, year after year. The sun a little dimmer or a little harsher depending on the season and the distance from the fissures. A haze so gradual that anything alive would have had no memory of a clearer sky to compare it to. There was no single terrifying moment. There was only a slow, patient rewriting of the air, one century folded into the next. What remains genuinely open is how much of the extinction these gases caused directly and how much they triggered through other chains of consequence. The warming oceans, the falling oxygen, the acid seas discussed elsewhere in this story. Some researchers treat the volcanic gas as the trigger and everything else as the aftermath. Others think the ocean's own chemistry, once disturbed, took on a life of its own and needed no further push. The rock remembers that the sky changed. It has not yet told us the full order in which the dominoes fell. $250 million years ago, the ground itself was not a quiet stage. It was part of the trouble under what is now Siberia, molten rock pushed up through cracks in the crust for what may have been 1 million years or longer. This was not one eruption. It was a slow, grinding flood of lava, piling layer upon layer across an area larger than some modern continents. If you had stood at the edge of that flow, the heat would have reached you before the light did. The rock beneath your boots would have trembled without warning, again and again, for longer than any single human life could span. There would have been no way to know when the shaking would stop, because even the land had no memory of stillness left in it. Geologists call this event the Siberian Traps, a name for the layered rock the lava left behind. One widely supported idea is that this eruption sat at the center of nearly everything else going wrong. At the same time, the lava did not just burn the surface, it also baked through thick beds of coal and salt buried underground, releasing huge volumes of carbon dioxide and methane into the sky. Some researchers estimate the eruptions may have released more greenhouse gas than the atmosphere had absorbed in tens of millions of years before it. This is where the ground connects to the sky, and the sky connects to the sea. The gases did not stay near Siberia. They spread slowly around the entire planet, thickening the air over every coastline and every open water. Carbon dioxide trapped heat. The oceans absorbed both the heat and the gas, and warmer water holds less oxygen, which meant the seas began losing their breath. At the same time, the sky was losing its balance. The connections did not stop there. Warmer oceans changed how water moved between the equator and the poles, weakening the currents that once stirred oxygen down into deeper water. Acid rain, formed from volcanic sulfur mixing with moisture in the air, may have stripped nutrients from the soil, which weakened plants, which loosened the soil further, which let rain wash even more of it into rivers and seas. Each system nudged the next. None of them acted alone. One competing idea holds that the eruptions alone, however large, may not fully explain the speed or scale of what followed. Some scientists point to the possibility of a large impact from space, though the evidence for this remains thin and much debated. Others focus on methane trapped in frozen ocean sediments, wondering if warming seas released stores of it that added another layer of heating on top of the volcanic gases. The honest answer is that no single cause has been proven beyond question. What most researchers agree on is that many systems failed together, each one leaning on the others like a row of dominoes made of stone, water, and air. Picture the chain this way. Deep underground, hot rock pushes upward. It burns through ancient coal. Gas rises into the sky. The sky grows warmer. The warm sky warms the sea. The warm sea loses its oxygen and its careful balance of chemistry. The chemistry shift changes the shells and skeletons that can form in the water. Nothing here happened in isolation. It moved through the earth the way a shiver moves through a body, one system passing its trouble to the next. If you had lived through even a small slice of this, you might not have noticed the volcano at all. You might have simply noticed the water tasting different, the fish growing scarcer, the air feeling heavier on a still afternoon. The scale was too large and too slow for a single lifetime to see clearly. Only looking back, across layers of rock laid down over hundreds of thousands of years, can we see the whole shape of the event. This is part of what makes the mystery so patient. It is not one broken piece we can point to and repair in our minds. It is a system of systems, each ordinary on its own, each capable of amplifying the others under the wrong conditions. The ground moved, the air thickened, the sea grew tired. Whether the volcano was the whole story or only the loudest part of it remains an open question, one that rock layers continue to hold on to, quietly, waiting for someone patient enough to keep listening. somewhere in the wreck of that dying world. The sky itself seemed to lose its patience. For a long stretch of time, storms did not come and go the way they do now. They simply stayed. Rain fell in heavy grinding cycles, and when it stopped, the air was thick and wrong, waiting to fall again. The cause traces back to the same volcanic gases that had already poisoned the oceans and choked the air with carbon dioxide. All that gas held heat close to the surface, and a warmer world moves more water through its sky. Warm air lifts more moisture. Moist air falls again as rain. Scientists studying rock layers from this period have found signs of massive, repeated flooding. Layers of sediment stacked like pages in a book no one wanted to write. If you had stood on a hillside during these centuries, you would not have seen storms arrive the way you know them, with a dark front rolling in and passing through. You would have felt the air stay damp for months, then years, the ground never fully drying, the rivers swollen far past any bank they used to know. Your skin would have felt the constant press of humidity, heavy and unrelenting, the kind that does not lift even at night. Geologists reading the rock in places like the Karoo Basin in southern Africa see this shift written in the stone itself. Below a certain layer, the rock holds the pattern of steady meandering rivers, the kind that took their time. Above that layer, the pattern changes completely. The channels turn braided and chaotic, cut and rebuilt again and again by floods too big and too frequent for plants to hold the soil in place. One idea is that this shift marks the moment vegetation itself collapsed across the land, since roots are what usually keep a riverbank from crumbling into confusion. Without root systems knitting the ground together, every hard rain became an event that reshaped the land instead of simply passing over it. But not every researcher agrees on how much of this pattern comes from lost plants and how much comes from rainfall intensity alone. A competing view holds that the storms themselves grew violent enough to rearrange rivers even where some vegetation survived, driven by a churning, overheated atmosphere rather than by bare soil. Both ideas point to the same unsettled world. They simply disagree on which failure came first, the sky or the ground. The pace of this change is hard to hold in the mind. These were not single storms remembered by name. They were climate patterns that lasted for thousands of years at a stretch, so slow that no living thing could have noticed the world was changing at all. A person standing in one century and a person standing 500 years later would have described the same rain, the same rivers, the same grey and swollen sky, even though the whole system had shifted beneath them the entire time. Some researchers have connected these endless storm centuries to what is called a hothouse climate state, a phase, where high carbon dioxide levels keep the entire planet locked in heat for far longer than a normal warm spell. In such a state, ice at the poles is scarce or absent, and the usual patterns that break up weather, the cool fronts, the seasonal turns, become weaker and less reliable. Storms build and do not release their energy the way they might in a more balanced climate. Instead, the same wet, heavy air seems to cycle in place, dumping its moisture over and over on ground already too saturated to take more. What remains unresolved is how widespread these storm centuries truly were. Rock records exist mostly where the right kind of sediment survived, and those places are scattered and incomplete. Whether every corner of the ancient world drowned in the same rhythm, or whether some regions simply grew drier while others grew wetter, is still an open question. One that different fossil beds seem to answer in different ways. It is possible the true picture was patchy, a shifting quilt of flood and drought, rather than one single storm that swallowed the whole earth at once. What is clearer is the pattern of change itself. Nothing in this era held still for long. The rivers rewrote their own paths, the rain rewrote the land beneath it. And somewhere in that grinding, centuries-long churn, the ground was being prepared, slowly and without witness, for whatever would come to live on it next. Picture the ocean 250 million years ago, somewhere far from any shore. The water is not black the way we imagine deep water tonight. It carries a strange green cast, faint and cloudy, like light passing through old glass. That color comes from something the water is missing. It is missing oxygen, and the tint comes from dissolved iron and sulfur compounds drifting in place of the gas that fish need to breathe. If you could hang suspended in that water, sunlight would still reach you from above, filtered and soft, but the light would fall on almost nothing. No schools of fish would catch the beams and scatter them into silver flashes. No coral would throw color back at you. The light would pass through and simply keep going, down into water that had not held a breath of oxygen in longer than anyone could count. Your body would not last minutes there, not from cold, not from pressure, but from the simple absence of the one gas your blood needs to carry to your brain. Researchers call this condition anoxia, a word that just means water with no oxygen in it at all. Evidence for it comes from the rocks themselves. Certain layers of stone from this period are dark and rich in a mineral called pyrite, which tends to form only when oxygen is absent. Fossils from these layers thin out and vanish. Whole communities of shelled and armored sea creatures that filled the oceans before this time simply stop appearing in the rock record, layer after layer, for what geologists estimate spans hundreds of thousands of years in some sections. One leading idea is that this anoxia spread from the deep ocean upward. Deep water is normally refreshed by currents that carry oxygen down from the surface in a slow circulation that can take centuries to complete. One loop. Some researchers propose that warming seas driven by volcanic gases in the air disrupted that circulation. Warm water holds less oxygen and mixes less easily with the cold water below it. If the mixing stalled, the deep ocean would have suffocated first, silently, while the surface still glittered in sunlight. A competing idea points instead to biology rather than mixing. Certain kinds of bacteria thrive in low oxygen water and produce hydrogen sulfide as a byproduct, the same compound that gives rotten eggs their smell. If these bacteria bloomed across large stretches of ocean, they could have poisoned the water further, spreading upward from below rather than starting there. Chemical traces in ancient rock, including sulfur compounds preserved for hundreds of millions of years, offer some support for this idea, but the traces are faint and open to more than one reading, and scientists still debate how much of the ocean this affected at any single moment. What almost no one debates is what light would have shown you had you been able to watch from above the waves. The surface would have looked deceptively normal blue under a pale sun, waves rolling the same way they roll tonight, only below. Past the reach of casual sight would the water have turned that ghostly greenish cast, the visible sign of chemistry gone wrong. Life clustered wherever a little oxygen still lingered, in shallow pockets near shore or close to the surface, wherever waves stirred air back into the water. Everywhere else, the light simply traveled through emptiness. This layered suffocation likely did not happen all at once. Some geologists think it came in pulses, retreating and returning over tens of thousands of years, giving brief windows where oxygen crept back, and a few species held on. Others argue for a longer, steadier decline, more like a tide going out and never quite returning. Both pictures agree on one thing: the change was too slow for any single creature to sense as danger. There was no darkening sky, no roar, no single moment of crisis, just water, generation after generation, holding a little less of what life required. If you had somehow stood at the shoreline through those centuries, you might have noticed only a strange quiet where the tide met the sand, fewer shells, fewer things moving in the wet edge of the world. The true story was happening out of sight, in water lit by the same sun, carrying the same waves, but slowly losing the one invisible thing that let anything breathe within it. How much of the ocean turned this way, and for how long, remains one of the harder numbers for scientists to pin down. The rocks hint at a wide reach and a long duration. The exact edges of that reach are still being drawn. Close your eyes and picture a shallow sea, warm and wide, stretching to a horizon with no land in sight. This is the world at the end of the Permian period, 250 million years ago. The water here does not look dangerous. It looks calm, almost gentle, catching a dull orange light from a sky thick with volcanic haze. But the temperature of that water is climbing, slowly, year after year, and nothing living in it has anywhere else to go. Shallow seas warm faster than deep ones. Sunlight reaches them fully, and volcanic carbon dioxide traps heat close to the surface, where most of the ocean's life actually lives. Some researchers estimate that sea surface temperatures in the tropics rose by 10 degrees Celsius or more during the worst of this event. Spread out over many thousands of years, 10 degrees sounds small when you say it quickly. Felt across a whole ocean, held for millennia, it is enough to unmake almost everything that swims, crawls, or roots itself to the seafloor below. If you had waded into that shallow water, it would not have hurt you at first touch. It would have felt like a warm bath, pleasant even, the kind of sea you might wish for on a quiet afternoon. That is part of what makes this mystery so quiet. There was no scalding wave, no sudden boil. The heat built the way a room warmed slowly through a long afternoon, degree by degree, until the animals that needed cooler water simply could not survive there anymore. Marine animals depend on oxygen dissolved in the water around them, and warm water holds less oxygen than cold water. So the heat did two things at once. It pushed some creatures past their limits for temperature alone, and it thinned the oxygen they needed to breathe, tightening a second noose around the first. Researchers studying fossil shells from this period have found chemical signatures, ratios of oxygen isotopes locked into ancient shell material that let them estimate how warm those old seas actually were. The method has real support, though the exact numbers still carry uncertainty, and different rock formations around the world sometimes tell slightly different stories about how fast the heat arrived. One idea, sometimes called the lethally hot ocean hypothesis, holds that shallow tropical waters became too warm to support animal life at all for a stretch of time, turning wide bands of the planet's shallow seas into places where almost nothing with a shell or a spine could persist. A competing view suggests the heat was severe but patchy, sparing pockets near the poles or in slightly deeper water, where a scattering of tougher lineages held on. Both views agree that the shallows suffered first and worst. They disagree on just how empty those waters truly became and how much refuge, if any, was left standing. Think about what this would have sounded like if sound could travel through time the way light does through old starlight. A healthy shallow sea is never silent. It hums with the clicking of shrimp, the scrape of grazing creatures on rock, the soft percussion of shells settling and resettling in sediment. As the heat pressed in this ancient sea, that hum would have thinned, then dropped, then in places gone quiet altogether, leaving only the slap of waves against an increasingly empty shore. No dramatic collapse marked the moment, just fewer and fewer small sounds spread across centuries, until whole stretches of coast carried almost none. Coral-like reef builders of that era, along with many kinds of shelled sea creatures, are thought to have been hit especially hard, based on how sparse or absent their fossils become in rock layers from this time. Some researchers argue this reef loss reshaped the shape of coastlines for millions of years afterward. Since reefs do more than shelter life, they also break up waves and build the physical structure of a coast. Others caution that reef ecosystems of this period differed enough from modern reefs that direct comparisons should be made carefully. The debate is really about how much we can say about ancient reef systems using what we know from reefs alive today. What stays open, even now, is the full pace of this warming, and whether it moved as one long slow ramp or came in surges separated by shorter pauses. Ice cores cannot reach back this far to give a precise yearly record, so scientists lean on rock chemistry that averages over stretches of time far longer than a human lifetime. That averaging smooths out any short bursts of heat that once might have felt sudden to a creature living through them. If you had stood on that ancient shore, waiting to see what would happen next, you might have waited far longer than any human life allows before the water finally told you the truth. The shallows had become a place that no longer forgave patience. Let's think about the deep ocean of that time in terms of numbers. Pressure in water builds by about 1 atmosphere for every 10 meters you go down. That is a simple rule, almost gentle in how evenly it applies. But follow that rule far enough, down past 1,000 meters, past 3,000 meters, and the pressure climbs into hundreds of atmospheres, pressing on every square inch of anything down there. Your body is not built for that math. At the surface, the air pushes on you with a force you never notice because you have never known anything else. Go deep enough into that ancient ocean, and the water would press on your chest with a weight equal to stacking a small car on every inch of your skin. Your lungs would fail long before the cold or the darkness became the problem. The numbers alone would end things quietly, without any drama at all. What makes this strange is that the pressure itself was not new. Oceans had always had a deep, crushing bottom. What changed after the extinction was what filled the water at every depth. Oxygen levels dropped through much of the ocean, sometimes to nothing at all, and the two problems stacked together. A diver from our time, dropped into that Permian to Triassic Sea, would face both the increasing weight of the water and a growing scarcity of breathable oxygen the deeper they went. Some researchers picture this as a kind of double filter, squeezing survivable space from two directions until only a thin slice of ocean, near the surface, still worked for animals that needed to breathe. There is a ratio worth sitting with here. Today, roughly 90% of the ocean's volume lies below 200 meters. In the dark, cold, deep water we rarely picture when we imagine the sea. In the aftermath of the extinction, large stretches of that same deep water are thought to have held little or no oxygen for extended stretches of time. If you multiply that fraction of ocean by the millions of years the crisis lasted, you get an almost incomprehensible sum. Enormous volumes of water, existing for enormous stretches of time in a condition hostile to almost anything that breathes through gills or lungs. Geochemists reconstruct these numbers through indirect evidence, not direct measurement, since no one was there with instruments. They study the chemical signatures left in ancient rock, tiny ratios of elements like sulfur and iron that shift depending on how much oxygen was present when the sediment formed. One line of evidence, drawn from black shales rich in these signatures, suggests low oxygen conditions across wide swaths of the global ocean for a very long interval. A competing line of evidence from different rock sequences in other parts of the world hints that conditions may have varied more by location and depth than a single simple number could capture. The overall picture holds, but the fine detail, the precise math of how much ocean was affected and for how long, remains an open calculation. Think too about how slowly this built. A 1 degree rise in ocean temperature, spread across 10,000 years, is a change of about 1/10,000th of a degree per year. No creature alive at any single moment could have felt that shift happening. And yet, compounded across the whole event, ocean temperatures in the shallow seas may have risen by several degrees, enough to lower how much oxygen the water could hold, tightening the mathematics of survival even further. Small numbers, repeated patiently across deep time, become enormous ones. If you stood at the edge of that ancient sea and lowered a hand into the water, you would feel nothing unusual in the moment. The temperature would seem ordinary. The push of the current would seem ordinary too. It is only when you multiply that single afternoon by hundreds of thousands of afternoons, each nudging the chemistry a fraction further, that the true shape of the disaster comes into view. The pressure of deep water, the falling oxygen, the rising heat, none of it required violence. It only required time, and enough of it. We are left with a set of numbers that describe a world hostile in a very particular way, thorough rather than sudden. Researchers continue to refine the exact figures, the exact depths, the exact durations, because the rock record is patchy and incomplete in places. What stays constant across every version of the calculation is the basic shape of the story: pressure from above, low oxygen from within, and heat working slowly on both until survival became less about strength and more about which small pocket of ocean still obeyed numbers a living body could bear. Picture a map of the world 250 million years ago, right after the Great Dying had done most of its slow work. Nearly all the land sat locked together in one huge mass, a supercontinent that geologists call Pangaea. Now picture most of the middle of that landmass turning to desert, not a small desert, the kind you might cross in an afternoon. A desert that stretched for thousands of miles, far from any coastline, far from any cloud that carried rain. The reason comes down to something simple and unforgiving. Water evaporates from oceans, drifts inland on the wind, and falls as rain. That the farther that moist air travels over dry land, the less water it has left to give. On a supercontinent this large, the center sat so far from any sea that almost no rain ever reached it. The rock record still holds the evidence today: layers of red sandstone, cracked mud, and salt flats that formed under skies that rarely wept. If you had stood in that interior, the ground under your feet would have been dry and cracked, stretching flat in every direction. The air would have felt thin and hot during the day, then dropped sharply once the sun went down, because deserts hold no moisture to trap the day's warmth. Your lips would have cracked within hours. Your body, built for a world of rivers and rain, would have found almost nothing there to keep it alive. This is where the mystery deepens, rather than resolves. Some researchers propose that the size of the desert itself helped drive the extinction that had already begun, by removing huge stretches of land where life might otherwise have clung on and recovered. Fewer green plants meant less carbon dioxide pulled out of the air. Less plant cover meant more dust, more heat reflected oddly, more soil lost to wind. Other researchers pushed back on this, arguing the desert was more a symptom of a changing climate than a cause of it, a landscape shaped by heat and volcanic gases that were already reshaping everything else. Which came first, and how much each fed the other, remains an open question the rock layers cannot fully answer. What both sides agree on is how narrow the margins were. A small shift in rainfall patterns, sustained over a long enough stretch of time, turned fertile ground into something closer to the surface of a place with no life at all. The plants that once held soil in place vanished, and there was nothing to stop the same process happening again nearby. It moved like a slow fire that never needed a flame, only dryness and time. This is the quiet lesson that sits underneath the whole extinction story. Earth's habitability was never a fixed setting. It sat, balanced on temperature ranges, rainfall patterns, and gas concentrations that could tip only slightly and unmake a world's ability to hold living things. The interior of Pangaea did not need an asteroid or a single catastrophic event to become lifeless. It only needed distance from the sea and time. Some scientists studying these ancient deserts wonder whether they hint at a threshold, a point past which a hot, dry climate becomes self-sustaining, hard to reverse even if conditions later ease. Others are more cautious, noting that Earth's deserts have expanded and shrunk many times across deep history without triggering runaway change on their own. The interior of Pangaea might have been an extreme case, a landmass so large it created its own worst weather, rather than proof of some hidden tipping point waiting in every desert. What stays certain is the scale of emptiness involved. For millions of years, a stretch of land larger than any desert alive today sat under skies that offered little relief and soil that held little promise. Whatever crossed it, if anything did, would have moved through silence, broken only by wind over dunes and the occasional rumble of far-off weather that never seemed to arrive close enough to help. Eventually, over spans of time too long for any single life to measure, the supercontinent began its slow breakup, and coastlines crept closer to what had once been hopelessly distant interior ground. Rain returned to some corners bit by bit. But before that happened, this desert stood as a reminder that livable ground on Earth has never been guaranteed everywhere at once. It has always depended on distance to water, on the shape of continents, on rainfall finding its way to soil that can use it, move those pieces even a little, and a green world can turn to dust that stretches farther than the eye or the imagination can hold. There is a strange idea some scientists have raised about the air during this long, slow crisis. Oxygen levels may have dropped low enough in certain stretches of time to leave the atmosphere sitting close to a threshold where fire behaves differently. Low oxygen does not sound dangerous at first thought. You would picture it as thin, quiet air, easy to breathe past, easy to ignore. But some researchers wonder if a low oxygen world, paired with a rise in other gases, created pockets of air that could catch flame in ways our modern atmosphere rarely allows. This is not settled. It is one thread of evidence among many, pulled from ancient charcoal and buried ash layers, and the picture it paints is still blurry at the edges. The clue comes from thin black lines in old rock, layers of charcoal that show wildfires swept certain regions again and again. Fire needs fuel, heat and oxygen in the right mix. Too little oxygen, and a fire gutters out. Too much, and it burns almost uncontrollably. Some geologists think the air during parts of this era swung through both extremes at different times and different places, never settling into the steady balance we breathe today. If you had struck a spark on a dry, resin-heavy plant in one of these windows, the flame that caught might have moved faster or slower than anything you have ever seen a fire do. This matters because oxygen was not falling evenly across the whole planet at once. It was patchy, shifting with the seasons of volcanic activity, with a slow burial and release of carbon in rock and ocean sediment. A place with slightly thicker plant cover might have held a slightly richer pocket of oxygen. A place stripped bare by heat and drought might have thinned out, its air leaning toward the flammable edge scientists still argue about. The unevenness itself is part of the mystery. Nobody has fully mapped how oxygen moved across the dying world, region by region, because the rock record from that time is scattered, worn, and hard to read with certainty. One competing view holds that the fire evidence has a simpler explanation: widespread volcanic heat alone, these researchers argue, could have dried out plant life across huge stretches of land, making ordinary fires more frequent without any unusual shift in the chemistry of the air itself. Under this view, the charcoal layers tell a story about drought and heat, not about a flammable atmosphere. The debate has not resolved. Both camps agree the fires happened. They disagree on whether the air itself was part of the danger or just a bystander to a drier, hotter world. Picture standing at the edge of one of these ancient fire zones. If your body could somehow endure the heat and the poor air, the ground would be dry and cracked, littered with the pale, dead stalks of plants that had given up trying to hold water. The sky above would carry a haze, not from smoke alone, but from the volcanic gases already thickening the upper air for thousands of years. A single spark, from lightning or from heat alone, might set off a fire that moved with a speed and hunger that felt wrong to you, felt faster than fire should be able to move. Your lungs, meanwhile, would already be straining, pulling at air that held less of what they needed and more of what they did not. What makes this particular unknown so quietly fascinating is how ordinary it looks from a distance. A wildfire is not a strange or alien event. Fires happen constantly across the modern world, and they always have. But the scientists studying this ancient stretch of time keep circling back to the same soft, unresolved question: was the air itself part of what let these fires burn the way they did? It is a question about chemistry, but it is also a question about what home means, about how small a change in a mixture of gases has to be before a familiar element like fire starts to behave like a stranger. No one has closed this question yet. The charcoal keeps its secrets, layer after layer, and the sediment records only fragments of what the air must have carried. Some researchers are still refining models of how oxygen and volcanic gases move together across those long millennia. Others are still gathering fresh samples from rock exposed only recently by erosion, hoping for a clearer signal. The fire lines remain dark and thin, pressed into stone that has waited 250 million years for someone to ask what kind of air could burn like that, and why. Let us think for a while about cold instead of heat. The world after the Great Dying was mostly a story of warming. Volcanic gases thickened the sky. Oceans lost their breath. But climate on this planet has never moved in only one direction. It swings over long stretches of time between warm and cold, and each direction carries its own kind of danger for a body like yours. Picture a different stretch of deep time, hundreds of millions of years earlier, when the Earth froze almost completely. Scientists call this the Snowball Earth, and the evidence for it sits in old rocks found near the equator, rocks that show the scrape marks of glaciers where no glacier should have reached. If the idea is right, ice sheets crept from the poles until they nearly met at the middle of the world. The oceans, if they still moved at all, moved under a lid of ice that may have been over half a mile thick in places. If you had stood on the shore during that frozen age, the cold would have reached past your coat, past your skin, into the marrow of your bones within minutes. There would have been no fire to build, because there was little dry wood and little shelter, only ice reflecting a weak and distant sun back into a colorless sky. Your breath would have frozen into a fog too thick to see through. The cold of that world was not a passing chill. It was a condition that no human body, with or without tools, could have outlasted for more than a short while. Not every researcher agrees on how complete this freezing truly was. One view holds that the ice locked the whole planet in a hard shell, ocean and all, for millions of years, a state sometimes called hard snowball. A competing view suggests a slush ball instead, with narrow bands of open or thin ice near the equator, offering a thread of liquid water where some life might have clung on. The rocks give hints, but not certainty. The question of just how frozen the frozen Earth truly was remains open, argued over in the same quiet, patient way as the question of how the great extinction unfolded 250 million years later. What ended the Snowball Earth may connect, in a strange and roundabout way, to the same slow chemistry that later filled the air with too much carbon dioxide. Volcanoes never stopped erupting under the ice, with no rain to wash carbon dioxide out of the sky and lock it into rock. The gas built up over millions of years until it warmed the planet enough to break the ice apart. In this way, the same greenhouse gases that helped end an ice age also helped end nearly all life. 250 million years later, the planet does not distinguish between too cold and too hot. It only responds to the balance of gases in its thin blanket of air, a balance so delicate that a shift of only a few degrees, held for long enough, can end a world. This offers a strange comfort and a strange warning together. The comfort is that Earth has recovered from conditions far outside anything a human body could bear. Cold enough to freeze the equator, hot and starved of oxygen enough to end most species alive at the time. Life found its way back both times, slowly, through lineages that happened to be sheltered from the worst of it. The warning is that recovery, on both occasions, took spans of time that dwarf all of human history. 10 million years passed before rich forests returned after the Permian extinction. Ice ages have come and gone across spans just as long. None of this means another Snowball Earth or another great extinction lies ahead on any particular schedule. The causes were specific to their own moments in deep time, tied to volcanic pulses and ocean chemistry that built slowly over spans the human mind struggles to hold on to. But the pattern itself, the idea that Earth's climate can swing to extremes nobody could survive and still find its way back to balance, stays true across the whole record of the planet. It is a pattern still being studied, still argued over, still only partly understood. If you let yourself picture that frozen shoreline, the wind carrying no scent because nothing green grew nearby, you get a small sense of just how narrow the space is where a body like yours can exist at all. Not too hot, not too cold, not too little oxygen, not too much acid in the sea. The window has always been narrow, and the planet has closed it before, in both directions, and opened it again in its own unhurried time. There is one more thing to picture before we rest, and it lives in the water itself. Some scientists who study this ancient extinction have looked closely at the chemistry of old seafloor rock, and they have found signs that certain shallow seas grew unusually salty and dense during this slow crisis. Warmer water evaporates faster, leaving behind more salt. Layer by layer, over thousands of years, some basins may have turned into something closer to heavy brine than to the ocean water we know today. If you had waded into one of these places, your body would have felt strangely light, held up by water thick with dissolved salt, the way it feels to float in the saltiest lakes left on Earth now. This is not settled fact. The evidence comes from scattered rock samples, from patterns in ancient salt deposits, from chemical traces that can be read more than one way. Some researchers argue that these hypersaline pockets were common and widespread, forming in shallow, cut-off basins as sea levels shifted and the water above them warmed. Others think these salty zones were rare, local exceptions, not a global feature of the crisis. The disagreement is quiet and ongoing, the kind that plays out in careful papers rather than dramatic headlines, and it remains open. What both sides agree on is simpler and stranger. Water this heavy with salt holds very little oxygen. The two problems layer on top of each other. An ocean already losing its oxygen to warmth and stagnation becomes even less hospitable when it also grows dense with dissolved minerals. For the creatures living in these shallow seas, animals with shells, gills, and simple blood chemistry built for a gentler ocean, the water itself became a kind of quiet trap. Not a wall of fire, not a wave of destruction. Just water that slowly stopped being able to support the delicate chemistry of a living body. Picture a shallow lagoon on that ancient coastline, its surface calm and glassy under a hazy dim sun. The water looks inviting from a distance, smooth and pale blue-green, but if you had lowered your hand into it, you would have felt how heavy and strange it moved, thicker than seawater should feel, resistant in a way that seawater is not. Beneath the surface, the world would have been mostly still. No darting silver flashes of fish schools, no green sway of healthy reef life, just quiet water. Salt crusting faintly at the tide line, and a silence that had replaced what used to be a crowded, noisy, shallow sea. This detail matters because it changes how we should picture survival itself. It was not always about being strong, or fast, or clever. Sometimes it was about which kind of body chemistry could tolerate slightly thicker, saltier, less oxygenated water for slightly longer than its neighbors could. A creature with a more flexible internal chemistry, one that could handle a wider range of salt and oxygen levels, might have simply outlasted others nearby that could not. Nothing dramatic happened to decide this. It was a slow filtering, done by chemistry rather than by claws or teeth. And here is where the widest view opens up. The salt in that ancient water, the calcium once locked in the shells of creatures who did not survive, the very atoms moving through that thickened sea, all trace back further than the extinction, further than the Earth itself. Every drop of salt water on this planet is made of elements forged inside stars long before our sun existed, and scattered across space, then gathered slowly into the rock and water of a forming world. The same atoms that once floated in that ancient lagoon are, in some form, still here, cycling through rock, ocean, and living things today. Nothing is created or destroyed. It only moves and waits, and sometimes gathers into conditions life can use, and sometimes gathers into conditions it cannot. That thought can sit gently with you as you drift towards sleep. The ocean outside your window tonight, if you live near one, carries salt and minerals older than the dinosaurs, older than this extinction, older than most of the rock beneath your own house. The story of that ancient, salty, breathless lagoon is not separate from you. It is one chapter in the same long chemistry that eventually became your bones, your blood, your breath tonight. Whether hypersaline seas were common or rare during that ancient crisis remains an open question for the scientists who study it. But the deeper truth beneath the debate does not need resolving to feel true. You are built from the same shifting, patient materials as that ancient, salt-heavy, silent sea. We have walked through a world your body could not have survived. The choking air, the sour, sunless seas, the long silence after almost everything died. Now, let's rest in one last quiet thought before sleep takes you the rest of the way. Picture the earth from far above, turning slowly in the dark. Not the earth of 250 million years ago, thick with poison gas and grey with dust. This earth, the one outside your window right now, blue oceans catching moonlight, thin clouds drifting over sleeping coastlines, a rim of pale air, so delicate from a distance, wrapped around the whole planet like a breath held gently in cupped hands. That thin blue rim is the only reason any of this is possible. The oxygen in it, the ozone layer, quietly filtering the sun's harder light. None of these things were guaranteed. 4 long stretches of Earth's deep past, that rim held a different mixture, one that would have ended you in minutes. Tonight, it holds the one mixture that lets you lie still, breathe slowly, and drift towards sleep without a single thought about the air moving in and out of your lungs. We do not fully know why the world tipped the way it did all those millions of years ago. One idea points to vast volcanic eruptions in what is now Siberia, pouring out gas for tens of thousands of years. Another points to the oceans themselves, losing their oxygen from the bottom up, until whole ecosystems simply could not go on. Some researchers think these forces work together, one triggering the other in a slow chain reaction across the whole planet. The full sequence remains an open question. What is not in question is the outcome. Something changed, gradually and almost silently, and the world on the other side of that change was nearly empty. And yet it filled again, not quickly, not the way a forest grows back after a single season of rain. It took millions of years, longer than any human civilization has existed, for the sound of a healthy world to return. Insects, birdsong, once birds existed to sing it, wind moving through full-grown trees. All of that came back slowly, patiently, without any plan behind it. The earth did not seem to be waiting for life to return. It simply kept turning, and life found its way back into whatever room the planet happened to leave open. That is the quiet thought, worth carrying into sleep tonight. The earth does not need you, or the sparrow outside, or the moss in the forest. The earth only needs its rock and its water and its slow, patient orbit. Life is the guest here, not the host. And yet, for reasons we still do not fully understand, this particular guest has stayed for billions of years, changing shape again and again, always finding some narrow window of air and warmth to fit through. You are living inside that window right now. Your heartbeat, slow and steady as you settle into the blankets, is only possible because of a string of conditions so specific that the universe did not have to produce them anywhere at all. And yet here you are, safe and warm, in a world that survived its own worst centuries and grew quiet forests and gentle oceans on the other side. Somewhere tonight, waves are moving under a dark sky, the way they have moved for longer than any memory can hold. Wind is crossing plains that no one is watching. None of it needs an audience, none of it needs you to understand it fully before it keeps happening. It simply continues, the way it has continued through fire and ice and silence, patient in a way nothing human can quite match. Let that be enough for tonight. Not an answer, just a picture of a small blue breathing planet turning gently in the dark, holding you the way it has always held everything else that managed for a little while to survive. Rest now. The air around you is the safe kind. The night is the calm kind, and the earth, ancient and unfinished and still full of questions, will keep turning long after you have fallen asleep. Subscribe for a brand new Earth topic every night. One tap and something wonderful is waiting for you tomorrow. Sweet dreams.